Dr. R. Sugaraj Samuel. He is working as a professor in physics at New College, Chennai. He is also training students for IIT JEE, AIEEE and BIT SAT. He has more than 16 years experience in both teaching and research. He has published a book titled The Complete Handbook of Bachelor of Electronic Science Practicals, which is prescribed for the syllabus for BSc Electronic Science by University of Madras. He has presented papers in several national and international conferences and has also conducted many training programs and workshops to motivate energetic students. His research areas are ultrasonic, polymers, crystal growth and photovoltaic systems. He is experienced in both regular classroom teaching and online teaching as well.
Welcome to UGC lecture series on oscillations and waves. We are learning about waves in this part of the lecture series. Let us see the session outline for today's lecture. In this lecture, we are going to learn about the pressure of a longitudinal wave and the concepts related to water waves and also the gravity waves and ripples. We have learnt about the types of waves. Initially, we have classified the waves as mechanical waves and electromagnetic waves, and mechanical waves as transverse and longitudinal waves. Lots of such classifications have been done. In this lecture, we are especially going to concentrate on the longitudinal wave propagation. About transverse wave also we have learnt lot of things. We have derived equation for even up to intensity, the wave, how it can be represented in the differential form. And in this lecture, the longitudinal wave is going to be learnt in depth. When we visualize a wave, normally the transverse wave only is quite easy for us to visualize. The wave propagates in one direction and the particle vibrates perpendicular to it. Both are very clearly represented also. Even when we take the snapshot pictures or situations, both the direction of propagation and the direction of vibration are clearly represented in the pictures because they are in two different directions. But when we consider the longitudinal wave, because the direction of propagation and the direction of vibration both are in the same direction, representing them in a pictorial form is slightly difficult, because snapshot cases will not help us to visualize the case with clarity. But in the case of longitudinal waves, the wave is progressing as compressions and rarefactions. This information we have learnt. So, let us recapitulate what is meant by compression and what is meant by rarefaction. So, this wave only, the wave is progressing, that is what is going to give us the base for further understanding. Pressure of longitudinal wave. We know that the longitudinal waves travel with compressions and rarefactions. In the region of compression, the vibrating particles are closer to each other, hence the pressure is high. In the region of rarefaction, the vibrating particles are far apart from each other and hence the pressure is low. Longitudinal wave is also called pressure wave. Because the compression and rarefaction is changing the density of the medium temporarily, and that is not termed as the change in density, but the pressure. When the longitudinal wave travels in air, especially gaseous medium, we could see the change in pressure, because pressure is a factor, is a characteristic of the gas. Mostly the wave prefers to propagate in the longitudinal form as far as the gaseous medium is concerned. Sound wave is a best example for that, but why the sound wave prefers the longitudinal form of propagation? We are going to learn about it with greater understanding when we learn about the concept sound. Under the topic sound, we will learn about all that, but right now only about the longitudinal, because we are yet to start the concept of sound. But before that itself, the pressure concept is to be understood in the longitudinal wave. So, that is why I have quoted the example of sound wave. Mechanical waves choose their mode of propagation depending on the medium. In solids, mechanical waves could travel both in the transverse form and also in the longitudinal form depending on the condition. We will learn about them in a separate lecture, but presently the compression and rarefaction produces a difference in pressure. That is what we have to keep in mind. The compression region, the particles are close, pressure is a particular value high, and the rarefaction region, the pressure is low because the particles are far apart from each other. Let us have a visual so that we could understand how the compressions and rarefactions are changing the pressure of the medium. See, this is the very clear visual, gives us an understanding how a longitudinal wave is progressing. It is progressing, look at any one compression, it is progressing in the positive x direction. Now, we have the compression and rarefactions shown here as a static or a snapshot case, and here is the compression existing, the particles are very close to each other. So, the pressure is high, rarefaction region they are far away, the pressure is low. How do we say when the compression is more, pressure is more? In the region of rarefaction the pressure is less. For pressure, the number of particles present is also a factor. How many number of particles? More number of molecules present in a closed container of gas, the pressure is naturally high. There are other factors deciding the pressure like the temperature and other factors, but in general it is a generic way of giving the explanation. More number of particles comparing to the next region, then the pressure is more than that region. That is how we give an explanation for this pressure variation. Is it possible to derive an equation for the change in pressure, the varying pressure? That is what is attempted in this lecture. So, let us see how the mathematical formulation is done to obtain an expression for the change in pressure that is happening in a longitudinal wave. Distribution of pressure. For a plane progressing wave, we have this equation. This equation is a very familiar equation which we have been using off and on in all the lectures. Y is equal to A sin omega t minus kx. This is the equation of a plane progressing wave which propagates in the positive x direction. If we differentiate it once, we get the particle velocity. So, that is also done here. The strain in the medium, for that what do? We differentiate it with respect to x. So, dy divided by dx we need to take. If we differentiate this displacement equation of the wave with respect to the term x, we get strain that is produced in a medium. This dy divided by dx is positive in the region of rarefaction, and this dy by dx is negative in the region of compression. Why? Because the variation dy divided by dx, if it is a positive value, it is a high value, it is rarefaction because more displacement dy is happening, and if it is negative of course, it is less, that is the lowest value. So, it is represented here, the dy is very less because the particles are close, it is representing the compression. The dy is very high, the displacements of the particles is very large. So, that is the region of rarefaction. So, this is how we have to explain for the sign of dy by dx. After obtaining the term strain for the medium due to the propagation of the wave, we will be able to get an expression for the pressure also. So, we need to relate the term strain and also the term change in pressure. If we go into the mechanics of the solid substances or materials, there is a term called bulk modulus. The bulk modulus is the ratio of stress to strain. If it is a bulk medium, instead of stress we can have the pressure there. So, that is what is the link between the pressure and the strain. So, in terms of the bulk modulus we can relate the change in pressure, which is nothing but the stress, and the strain is dy divided by dx. So, that is what is discussed now. We can try to relate them. This is how the two are related. The bulk modulus B of the elastic medium is defined as the ratio of change in pressure to the volume strain. So, we have brought in the dP here. The minus sign says the definition, when the pressure is decreasing, the strain will increase. So, these two are varying in a opposite sense. So, that is the meaning of this minus sign. So, we can rewrite this equation for the change in pressure dP. So, dP is equal to negative of bulk modulus multiplied with the volume strain dy divided by dx. So, when we write this, we will be able to obtain an expression for the change in pressure. This shows that if dy divided by dx is negative, dP is positive, because there is a minus sign relating the two at the region of compression. The same way, if dy by dx is positive, the dP becomes negative, it is the region of rarefaction. So, this is how we could interpret the relation between the strain dy divided by dx and the change in pressure dP. So, this equation is going to be the typical tool in relating them. Now, we have to substitute for dy divided by dx, which we have done before. Let us do that. Differentiating the simple harmonic motion with respect to x, that is done here. We have taken the basic wave equation for displacement and differentiated with respect to x, that is what is substituted for the change in pressure equation. So, we finally obtain this equation. Here the minus sign gets cancelled, because when we substitute for dy divided by dx, there is already a minus sign. And when we have a look at this equation, left hand side we have the change in pressure. On the right hand side, what is there here? B, K, A. Here B is the bulk modulus, K is the wave number, A is the amplitude. So, this could be written as dP 0. Here the suffix 0, when we write it, this is the maximum change in pressure. This is change in pressure, dP is change in pressure, dP is maximum change in pressure. I would like to highlight upon these two equations. The first equation, have a look at it. Here you have y as the displacement, A is the maximum displacement. The same way here dP is the change in pressure, dP naught is the maximum change in pressure. So, these two have some sort of similarity, except for the sin factor and the cos factor. There is a similarity between the two equations. So, what is the conclusion? How the displacement is changing with respect to x and t, with respect to the space and with respect to the time, the pressure is also changing with respect to the space and time. We have got the dP equation as a sinusoidal equation. It is dP naught cos omega t minus kx. If it has that form, we can definitely believe that the pressure is also varying with respect to time and with respect to space, and we can try to find a relation or try to explain the manner in which the variation happening in the displacement and the change happening in pressure. Shall we do that? Let us have a look at the visual. This helps us to get an understanding. As the displacement varies, the pressure is also varying. Comparing the displacement and pressure equation, we show here the two. The solid dark line shows the displacement of the air, and the dotted line, orange line, shows the variation, air pressure variation. At this juncture, we have to be little careful. This is just the representation of the variation happening. It is typically not the direction of variation, how the value is increasing and then decreasing, how it is increasing, that is not the typical appearance of the wave propagation. Wave propagation is like this, it is moving. When the wave is propagating in one direction, the particles are moving in the same direction. Wave is propagating in this way, the particles are vibrating in this manner. But this is a graph showing the maximum and minimum. Here there is a maximum and there is a minimum. So, we should not get confused by looking at this equation. It appears as a transverse wave. It is just a representation for the displacement which is happening in the direction of propagation only. It is not vertical to the direction of propagation. We should not have that kind of misunderstanding by looking at this representation. Still, the wave is a longitudinal wave, that we have to keep in mind. Only the representation is done because we cannot show both variations happening in the same direction. That is why we represent it in this way. And there is a phase difference of pi between the sine and cos waves. This gives us the understanding sine wave and cos wave will have a phase difference of pi. The pressure is moving ahead with respect to the displacement. There is a phase difference of pi which is obviously seen in this representation. So, we have proved that in a longitudinal wave there is a pressure variation that is propagating in the direction of propagation. So, this is another level of understanding the wave propagation. It is not only the displacement that is varying in the direction of propagation. Because of that, the pressure is also varying in the medium as far as the longitudinal waves are concerned. We can try to establish a relation between the maximum pressure that is happening and also the displacement that is happening in a wave. So, let us look at the relation to have an understanding. The relation between the maximum pressure variation and the maximum displacement, which is called the amplitude, is shown here. dP naught is equal to BKA, which we have replaced in the earlier equation. The pressure variation and the displacement are related with the property of the medium. Here B, bulk modulus, is the property of the medium and K is the wave character and A is also wave character. It is the amplitude and K is the wave character. So, in a nutshell, the relationship is established with the factors related to the medium and also the wave. So, they are establishing the relation. we have arrived at the expression for the pressure wave, the pressure variation that is happening in a medium. Why this is done? Why the pressure variation is to be learnt? When we study about the sound wave that is propagating in a wave in a medium like air, it is producing the pressure in the medium. So, we should know the basic concepts related to the pressure variation happening when a wave, longitudinal wave propagating in a medium. This pressure variation is only travelling in space, especially air medium, and it affects the receiver. As far as the sound wave is concerned, the sound waves affect the diaphragm of our ear, and that is sensed by the nerves, the hearing nerves. They transmit the signal to the brain and recognizes the voice and so on. So, this pressure variation has to be learnt thoroughly when we want to have an understanding about the sound propagation, especially about the longitudinal way of wave propagation. Now, it is time for us to learn some concepts related to the other form of wave propagation, like how the ripples are formed in water surface, whether the same type of waves are propagating in the interior of the water medium and on the surface. So, let us have some basic concepts related to the water waves. In general sense, waves formed on the surface of water is quoted as an example for transverse wave, since the particles on the surface move up and down. The up and down motions formed on the surface of water are called ripples. If the restoring force acting on the particles are due to the elastic property of the medium, then the bulk modulus of the water, that is what is bringing the particles back to the original position. The water medium has the elastic property, it has bulk modulus. Because of that elastic property, the particle, the water molecules or the region which is vibrating is coming to the original position, which is giving the restoring force. We already have quoted several times the ripples that are formed on the surface of water, the best example for transverse wave, because a cork that is made to float on the surface of water will move up and down. The cork will not progress, only the ripples will progress, the cork will remain there moving up and down. What is responsible for bringing the cork back after it is displaced? It is the elastic property of the water medium, but it is happening on the surface. When we go deeper into the water, or the elastic properties alone responsible for the restoration? No, the gravity is there, wind is there. So, there are lots of other factors governing in restoring the displaced particles of water or the molecules of water to come back to the original position. So, restoring force is not just due to only the elastic property, it is governed by various other properties in practical sense. So, we will learn about that in more details now. So, this visual gives us how the ripples are on the surface of water, but in practical case the restoring force of the displaced water is not only due to the elastic property of the medium, it is also due to the factors like gravity and also the wind, which is always blowing above the surface of water. Hence, the wave no longer is pure transverse, it is slightly complex in nature. if the elastic property is alone responsible for the restoring force, then it is a perfect transverse wave. But because of the presence of the role played by the gravity and also the wind, the nature of the wave is slightly complex. That is going to be learnt further. In fluid dynamics, gravity waves are waves generated in a fluid medium or at the interface between two media when the force of gravity or buoyancy tries to restore equilibrium. An example of such an interface is that between the atmosphere and the ocean, which gives rise to wind waves. This kind of impact produced by the gravity and the wind are felt very much in ocean, where the water is available at vast expense. A gravity wave results when the restoration of the fluid to equilibrium produces a movement of the fluid back and forth, which is called wave orbit. The gravity waves on an air sea interface of the ocean are called surface gravity waves. When it is happening at the interior, it is called internal waves. Wind generated waves on the water surface are examples of gravity waves that forms the tsunami and ocean tides. See, this visual gives us understanding of how the wave is formed. There are several terminologies which come across, like capillary waves, ripples, chop, wind waves, fully developed seas, and then swells. It is shown here, it is varying with respect to the length of fetch. It is pertaining to the seashore. Now, we will see some basic definition about the each terminology we have come across. The capillary wave is a wave travelling along the phase boundary of a fluid whose dynamics are dominated by the effects of surface tension. So, when it is far away from the shore, the surface tension plays a vital role in making the waves possible in that region. When we come further closer to the shore, a ripple is formed. This ripple is a small wave or series of waves on the surface of water, especially as caused by slight breeze or wind. So, when we move towards the shore from the interior of the sea in a particular region, only due to the surface tension the wave action is generated. It is called capillary wave. Why capillary? Because in capillary action the surface tension plays a role. The capillarity itself is due to surface tension. So, it is called as capillary wave. And when we move closer further towards the shore, the wind develops the wave further, which are produced due to the surface tension. Let us see what is the next term, which is called chop. It is also known as wind chop. That means it is cut out, it is closed out. This is a wave that breaks along the entire length, at the same time making it unsurfable. It is also called shutting down. Now, the wind further chops off the wave, it is breaking the wave, the entire length is broken, and finally we have a term called swell. In swell, it is a series of mechanical waves that propagate. The swells to be better sorted and free of chop as they travel towards the coast. So, in each stage the gravity and also the wind, they play a vital role, and earlier it was also partly due to the surface tension. So, all these factors govern the wave propagation as far as the ocean waves are concerned. There are few visuals which we would quickly have a look at and then wind up the session. This helps us to see how the gravity wave is propagating. It is now called gravity wave because the gravity governs the nature of propagation, and at the depth the circles are small. When we come to the surface, the circles are more. I think we have come to the end of this lecture. Let us see the summary of this lecture. In this session, we have seen the concepts of pressure of a longitudinal wave, water waves, gravity waves and ripples. Let us test our understanding by answering these questions. Explain the pressure variation happening in a longitudinal wave. Deduce the equation representing the pressure variation and compare it with displacement equation. Explain the different stages of ocean wave formation. So, with this I would like to wind up this lecture. See you in the other lectures with more concepts about waves. Thank you.